nanoHUB.org.
Online simulation and more for nanotechnology.
We keep looking at plasmonics and metamaterials enabling nanophotonics. So let me just briefly reiterate the advantages of plasmonics. So they are good in terms of optical processing of data, because with plasmonics you could enable much denser recording of information, because plasmonic antennas could be exceptionally small and locally increase fields or temperature, and that allow you denser recording of information. And that's of course related to the fact that they provided sub-wavelength confinement. And that's the key thing about plasmonics, the fact that they could bring light down to nanoscale. And the thing is that in any electronic circuitry, the electrodes are already there, they are metallic, and as well as conductors. And the point is that there are good conditions for hybridization. There are metallic parts which also could play a role of plasmonics. So plasmonics could be used for coupling on other on-chip devices by using this surface plasma polaritone. In this case, by propagating these SPP waves, you could provide coupling between different components. So in general, you could say that plasmonic could be used for guiding, detection, modulation, sensing. All these different ingredients are very important to enable all the complex functionality of plasmonics. And of course, plasmonics could result in enhanced local fields, which are in the heart of nonlinear optics, because nonlinear optics requires relatively high fields, and that's what plasmonic enables. And in that regard, it's very important. In turn, nonlinearities are critical to realize switching, which of course is in the heart of any logical operation. So as I pointed out, it could be integrated with electronics, which is a big advantage. So plasmonic could be used for nanoimaging and spectroscopy, data recording I already mentioned, for sensing, including surface-enhanced Raman scattering, for photodetectors, which would be extremely small, much smaller than the wavelengths, and for all type of biomedical applications. So that's all generally motivation for plasmonics and metamaterials, which artificially designed structures that quite often have these plasmonic components. This is just a brief recapitulation that what plasmonics enables is confinement light down to nanoscale, and here you could see some examples realized in our lab. So you could make this bow tie-like antenna with exceptionally small gap in between, and the local field in the gap between these two metallic parts could be 4 to 5 orders of magnitude in terms of intensity higher than the intensity of the incident field. This is simply the effect of resonance, when in the course of time you accumulate energy, and as a result you have here exceptionally high local fields, which would be great for many applications I just mentioned, ranging from sensing, data recording, high nonlinearity, switching, and all other related things. One of the key things about these plasmonics, that they could be used for nanoscale lasers. And that's actually a very important ingredient of future nanophotonics circuitry. One could say that arguably one of the greatest devices created by humans is MOSFET, because this is certainly in the heart of electronics. And the role of MOSFET in case of nanophotonics would be play this nanoscale laser, because it would provide exceptionally small source of coherent radiation. And since it's a nonlinear device, it could be used for all type of nonlinear switching. And so I'm saying that it could be played a similar role in case of nanophotonics as MOSFET plays in case of electronics. In terms of theory behind this nanoscale laser, which sometimes is called SPASER, SPASER stands for surface plasma amplified stimulated emission radiation. Like laser, instead of in the word laser, the first L stands for light. Here, instead of light, we have surface plasma. So the idea here is that to have lasing, you need to have two critical ingredients: amplification, gain, and a feedback system. This is a good example when actually I mentioned that the absence of sufficient dialogue between engineers and physicists resulted in delay for 40 years discovery of this very important device like a laser, because feedback system has been known for several centuries. Engineers use it everywhere. And of course, stimulated emission is known since 1918 when Einstein described it. And it's so obvious if you have stimulated emission which produce photons identical to those photons which stimulate that emission. And if you have feedback system which could basically make this amplification multiple times by making light going over and over again through amplifying medium, you would get these laser oscillations. However, it was delayed because of the lack of communication. Therefore, I keep repeating, please do cross-border of whatever research field you're working in. And that's where the best fruits are. So you need these two things, gain and feedback system. How to make feedback system smaller than λ/2? Because typically feedback system is some kind of resonator cavity, and the smaller size we know is λ/2. So cavity typically operates like the size should be integer number times λ/2. And that's the condition when wavefront would completely restore after one round trip. And so, but lambda is around 1 micron, λ/2 it's still sub-micron, but certainly not nanoscale. And the idea behind of this nanolaser, which as I said theoretically was proposed by Stockman and Berman, is to use to get feedback system not for light per se, not for photons, but for surface plasmons. Remember, surface plasmons, it's still electromagnetic oscillations at optical frequency, but they are confined much stronger. So if you would amplify if you have feedback system for surface plasmons, then it could be nanoscale. And if you amplify the surface plasmons and then convert it into photons, that would be your nanoscale laser. And actually the very first nanoscale laser, which would be really small in all three dimensions, was realized in our collaborative work done between Norfolk State, Cornell, and Purdue. So here you could see our nano laser. In the core, it has this gold sphere, which was only 14 nanometer in size, 1/4. And around you have this dielectric shell, which doped with active material dye. When you optically pump dye, it provides amplification. So, but what you amplify is surface plasmons, and you have these feedback systems for surface plasmons inside of this gold core, and then you convert it to light. So that was the first demonstration of nanoscale laser. By the way, it still remains to be the smallest laser ever demonstrated. So the whole size was like 40 nanometers, with, as I said, 14 being a gold core and 40 is the shell with active material. So there is also some other versions of nanoscale laser. This one done by Shang Zhang in Berkeley. He used this semiconductor rod and metallic film. And optical mode was largely so-called hybrid mode. It largely concentrated between this semiconductor rod and metallic film, and when it propagates, it gets amplified by this optically pumped cadmium selenide nanowire. So, and that nanolaser worked at relatively low temperature. Then they generalized it and used this kind of plate, and that enabled room temperature nanoscale lasing. So it's still very large activity, how you could make it electrically pumped, and how you could make it really small, how you could make it out of materials which is the most compatible. But the idea here that to have this spacer or nanoscale laser, it's very important for nanophotonic circuitry. It also could be enabled surface plasmon, because surface plasmon provide this confinement on nanoscale, and then you could have this feedback system on nanoscale. So other applications related to plasmonics and which enable key ingredients for nanophotonic circuitry. Of course, modulator is a very important part of any circuitry, electronic or photonic. In this case, we speak of nanophotonic circuitry. A rather elegant idea was proposed by Shang Zheng's group in Berkeley, I mentioned him already, which combines graphene. It's indeed a wonderful material, 2D material. And so specifically what they suggest to do is to take this silicon waveguide. It's, as we discussed last time actually, of course, you could use surface plasmons as interconnects to propagate information, but still losses are significant, and you could propagate it for several microns, but not for longer distances. In that regard, of course, silicon waveguides might be a good idea to use. So to basically to do all this switching, processing on nanoscale by using plasmonic structures, but propagate using by the silicon wires, as sometimes they call them, but they're wires for light rather than for electrons. So, and the idea in this particular case, how to make out of this silicon wire a modulator, it's to put graphene right on top of the silicon waveguide. And if you look at the field distribution in this silicon waveguide, it's actually concentrated largely right in the area where graphene is. So why it's important? Because in graphene, you could easily move the Fermi level by simply applying voltage, by biasing it. And because of the band structure of graphene, this conic-like type of structure, which has this Dirac point, the famous Dirac point, so the interband transition can occur only when the photon energy is larger than 2 times Fermi energy. So which means if you have a situation like this, when the photon energy is actually smaller than Fermi energy, so you would not have interband transition in graphene. Because you don't have interband transition, light is not absorbed, transmittance through this structure is high. So whereas in this situation, which you could accomplish by simply changing the voltage, the Fermi energy is less than half of the photon energy, so that interband transition occurs because of the absorption transmittance drops. So you could electrically modulate and let more or less light going through this silicon wire or silicon waveguide. So that's of course elegant because it combines graphene, it's a wonderful material, and you could control optical properties electrically. So that's a electrically controlled modulator. So that's relatively old already works in that. People suggested a different modulation. It's more efficient because you should remember that absorption of graphene is relatively small, around 2%. So, but there are ways to increase it by, for example, nanostructure, nanopatterning graphene. So people actually work in this and similar directions to have this type of modulator. But this is at least an example how you could make modulators out of this. Another application using plasmonics and graphene as well, it's actually graphene-based photodetector. In this case, you have these plasmonic antennas, which are just basically gold discs. This work done in group led by Naomi Hallas in Rice University. So, and it's sandwiched between 2 graphene sheets. So what happens when you radiate light, you could induce this, you could create this electron hole pairs in graphene that eventually could be detected. That works as a photodetector. But the role of these plasmonic antennas is that they enhance local fields, and therefore this creation of electron hole pairs becomes more efficient. Because in the vicinity of antennas, local fields are high, therefore you create electron hole pairs more efficiently. It's one thing, and another thing which is actually even more important, that these plasmonic excitations in gold antennas could directly decay into electron excitation. So you excite these collective excitations of electrons, which are plasmons, surface plasmons, and they decay into 1 electron excitations in graphene and create electron hole pairs. So that's it's called hot electron generation by decaying surface plasma. And it turns out this process is extremely efficient. And as a result, you have a very efficient, in this case, 20%, I would say reasonably efficient, that could be actually further enhanced, photodetector based on graphene and plasmonic antennas. In our group, my student, Di Wang, actually, along with Gerard Fan, did work how to make actually this photodetector really efficient. And the used idea, which comes down to my early work, I have been working for a long time on fractals, and fractal structure, which is scale invariant structure, because of their scale invariant symmetry, they kind of promote localizations. So if you make a plasmonic structure with fractal geometry radiated with light, then excitations tend to be localized in very small areas called hotspots. And when you change the frequency of polarization, you decide different hotspots. But again, because of the scale invariant symmetry, in this case you have snowflake-like structure, which is kind of self-similar, looks similar in different scales. So, and because of that, you have this localization, you have these hotspots, and in the end of the day, you have extremely broadband absorption. And why you need it? Because with graphene, as I said, absorption is relatively small, 2.3%. Broadband, but small. So people do use plasmonic structure, like in the previous slide, gold antennas, but they still enhance in a relatively narrow spectral range. Whereas with fractals, as I said, because there is different parts of fractal resonate at different frequency, altogether, fractal actually resonates in a very broad spectral range and flat. So the absorption spectrum of fractal looks very flat, polarization independence, almost a polarization independent because of this symmetry, and providing absorption and enhancement in a very broad spectral range, because these hotspots have very high local fields, therefore they're called hotspots, and therefore provide enhancement. And by different wavelengths, you create different hotspots and provide enhancement at these different spectral regions. So altogether, you cover a very broad spectral range. This is SEM image of fractal structure, which we nanofabricated. It's a snowflake, and you could see that self-similar. The whole structure looks like this. This smaller looks like the whole structure, and this even smaller also look the same. So you have the same pattern on a progressively smaller scale. That's what self-similarity about. That's what fractal means. So, and as I said, the beauty of this, you could get enhancement as opposed to this simple plasmonic structure in a very broad spectral range. And that's what we obtained. We compared actually this photovoltage generated when you irradiate structure with light for bare graphene, just sitting on a substrate, and for graphene sitting on a fractal structure. And you could see that the enhancement is quite significant, around factor of 10, and it's almost frequency independent. And there is some, because gold actually has interband transition. This fractal structure was made out of gold. And because of interband transition, in this shorter wavelength, there is some heating effect, and therefore enhancement is somewhat less. If there wouldn't be interband transition, that would be basically almost flat. So, and it almost doesn't depend on polarization angle, which is really good. So it provides this enhancement roughly one order of magnitude in the broad spectral range. And this is absorption of fractal itself. You see, it's very broad and flat. So it means that it would provide enhancement in this broad spectral range. So this is an example how you combine different ideas. In this case, localization in fractal structures actually turns out to be Anderson type of localization, similar to Anderson localization for electrons. We have here Anderson localization for surface plasmons, as we showed quite a bit ago with my collaborator, Andrei Sarachev. So it's Anderson localization for surface plasmon, which results in these hotspots providing enhancement in a very broad spectral range. And this idea here is combined with using graphene as a photodetector. So there are lots of activities to use plasmonics for photovoltaics. And the three key directions to use for the plasmonics for photovoltaics, as described in this nice review done by Harriet Water from Caltech and Albert Polman from Amolf in the Netherlands, are summarized here. You know that if you use silicon as photovoltaic cell, it has high refractive index, meaning that lots of light is reflected. So because impedance mismatching, you could say. So lots of light is reflected. By introducing these particles, you actually you make this broad angle scattering. So large angle broadband scattering. And because of that, you effectively increase the propagation length for photons. One of the biggest problems for photovoltaic cells is the propagation is photon mean free path. It's much larger than charge carrier mean free path, meaning that you do not absorb photon on the scale where your charge carrier propagate. So that's why you don't have enough efficiency. So if you would enforce absorption of photon, if you would make mean free path of photon matching the mean free path of charge carriers, then the efficiency would be optimized. So in other words, you need to increase harvesting of photons. Well, in this case, instead of photons being reflected, they actually, because of this large angle scattering, they would be more efficiently harvested. That's the idea. Another idea, because they're plasmonic structures, result in higher local field, you could generate electron-hole pairs more efficiently, simply because you have higher local field. Similar idea. And yet another approach to make this periodical gradient in metal structure, and because of that, you could excite surface plasmon polariton. Remember, we need to have these periodical modulations to match, to conserve momentum, because the photon momentum is too small to excite directly the surface plasmon polariton. Therefore, you need to introduce gradient. And by doing so, you excite surface plasmon polariton, and again, you have this propagation through photovoltaic cell for longer distances. Basically, you optimize harvesting of light by exciting the surface plasmon polaritons. So I'm not sure it would work for silicon, because with silicon photovoltaic cells, there are actually different things which control the market nowadays. It's like cheap way to produce it by using amorphous silicon in China and so on. Market is a very complicated things, but at least in principle, and if it's not silicon, but rather low efficiency photovoltaic cell, like organic based photovoltaic cell, plasmonics in principle could increase the efficiency of the generation of electrical energy for sure. And that's at least in general possible approaches to accomplish this. Yet another thing which plasmonics, by showing all this, I want to emphasize that the role of plasmonics and metamaterials goes far beyond to just nanophotonic circuitry. There are many other applications. Like this one is basically to control thermal radiation. We have this perception that, well, black body radiation is so fundamental, you cannot really much do about this. It turns out that it's not true, and actually you could control thermal radiation to a huge extent. There are lots of activities now to engineer thermal radiation, and of course there are many, many important applications, including defense-like applications. You know that human body temperature is around 10 micron. If you would be able to control, to detect radiation around 10 micron, you could develop better night vision goggles, many applications. So like you could see hot engine, in this case the temperature, let's say, is 5,000 Celsius. You know the black body radiation for 5,000 Celsius, how you could control, engineer that. So there are many applications, or just even simple example, like these smart windows, light goes through the windows, it heats up the room, how to keep it cool, or the other way around. It's all about controlling thermal radiation. And now we are getting to the stage that there are lots of things could be done in that regard. And there are lots of activities around the world. And in my group, we're also doing some work related to this. So you could, first of all, you could match impedance. When you match impedance, light is not reflected. It means that all either transmitted or absorbed in your structure. That's one thing to do. By introducing this whole type of resonance structures, like here you have a single resonator, here you have double resonators at two different frequencies. So you actually could dramatically modify the thermal radiation. So you know that according to Kirchhoff's law, emissivity is equal to absorptivity and to absorption, and they match each other. When you have this single resonance structure, you could compare it at different temperatures. This is black body radiation at this is black body radiation at 300 Celsius. Here you increase temperature, and you could see how dramatically emittance actually are different from emittance of black body radiation. Or with this double resonance structure, you have these two peaks in emissivity and emittance, and it's of course dramatically different from what you get for black body. And as it should be according to the Kirchhoff's law, emittance matches impedance, absorptance, so they almost the same. So the idea, by introducing all these resonance structures, you could actually dramatically modify thermal radiation and control it. It's a very attractive feature, actually. Jingjin Liu in my group did this actually very nice work. by demonstrating that the extent to which you could control this thermal radiation, because we have this perception that thermal radiation is incoherent. It's due to spontaneous emission. It goes in all the directions. There are no any coherence whatsoever because it's black body radiation after all. So what she did, she made this grating on the surface, and this of plasmonic structure of titanium nitride actually. Why titanium nitride? Because if you use gold and silver, which have rather high surface energy, then thermal heating leads to dewetting and formation of metal islands. Whereas with transition metal nitride, such as titanium nitride, it provides stable, coherent thermal source. Remember, this titanium nitride is a very refractory material which can sustain very high temperatures. So, and surprisingly, as opposed to intuition that it should be broadband with no coherence, we obtain actually very high coherence both in space and frequency domain. So in terms of frequency domain, you could see that it's a very sharp radiation actually. In this case, it was designed to center around 3 micron. So you see how dramatically you could modify the thermal radiation. You heat it up, instead of having this broadband radiation, you have the radiation, thermal radiation, which is peaked around 3 micron. And that occurs because you excite these antennas made of plasmonic materials. So they resonate at 3 micron and you have this peak in emission. But you also have very high spatial coherence, which is manifested itself through this very narrow angular radiation. Because of this surface plasmon polaritons, because of this symmetry, radiation all goes in the normal directions. And with very narrow angular distribution, just around 1 degree only. So it's very coherent, well, let's say quite coherent, both in space domain and in the frequency domain, despite the fact that we are talking about thermal radiation. So this idea that you could control, design, and engineer thermal radiation is very attractive, and that's all due to these unique properties of plasmonic materials. So let me make a parallel with silicon electronics, and to emphasize the importance of developing new materials. I reiterate this message through the course actually repeatedly, because I think it's really important for us to understand it. Similar to silicon, when basically people realize that silicon is material of choice for electronics, but since that time actually lots of different materials have been introduced to broaden the arsenal for electronics. Now you have many elements from the periodical table of elements which contribute to this nowadays electronics. And until very recently, when it comes down to plasmonics, people basically use almost like exclusively gold, sometimes silver, but silver is not chemically stable. You have to protect it. So we need to do similar type of job to broaden the scope of plasmonics, because this is in the heart of nanoscale photonics. So, and then that's actually the way to bring it to real life applications. And in that regard, it's important to broaden the family of material that could be used for plasmonics. And my colleague Alexandra Baltasova, she's actually pretty much a pioneer in that area, even though now a number of groups now working in different areas to broaden the scope of material platforms for plasmonics. This work they did with Harriet Water, for example, from Caltech, so where they showed that, of course, indeed, there are a number of different classes of material that could be used for plasmonics. When you speak of, for example, of mid-infrared materials like perovskite, actually could be pretty good plasmonic materials. The same perovskites which now are used for all type of photovoltaics, actually. And in terms of near-infrared, I already mentioned transparent conducting oxides actually look very promising for plasmonic materials, and they could be switchable, tunable, have lots of advantage over gold and silver. And in terms of visible, as I pointed out, these transitional metal nitrides. So the point is we are not limited by gold and silver. So there are many classes of other materials to explore, which actually could have and do have advantageous properties over traditionally used plasmonic materials. And to further emphasize the importance of materials, I bring this gentleman who won the Nobel Prize one could say, the ultimate prize in science in different years. And all this work is related to development of materials. Well, including this relatively recent 2013 Nobel Prize in Physics for developing blue LED, one could say, hey, what's so special? There was green and red, and they developed blue LED because it was critical, because with all the colors you could now reproduce this white light, and that was so important that they quite for a good reason got the Nobel for developing this blue LED. Of course, graphene work, it's just yet another material, and strictly speaking, it has been known quite for a while before these two gentlemen, but they were able to isolate this and to study carefully its unique electronic properties, and that resulted in yet another Nobel Prize. And this is actually, one could argue, hey, low loss optical fiber, it's just a fiber. What they think they did, they just decreased losses in fiber. But that's enabled the whole optical communication. Now we send signals over sea, and we actually could send information for so huge distances. That's changed the world. So that's a beautiful example how new materials make a truly disruptive change in terms of technology. So therefore, it's indeed very important to develop new material platforms for plasmonics, metamaterials, nanophotonics, and that's actually makes a big difference. So, but what's the problem with gold and silver, which have been used, these two materials, largely for plasmonics? Of course, they have high cost. Their optical properties are not adjustable. So basically, the plasma frequency is fixed. We have this 10 to the 22 or so charge carriers per cubic centimeters, and that's it. You cannot really modulate it much or change it. They're not CMOS compatible. That's very important. It doesn't sound like science, but it is important because, I mean, you have this industry used for semiconductor, and semiconductor industry, you cannot just bring new material and put in the same fabrication line. They cannot sustain high temperature. I already mentioned that when plasmonics concentrates energy within very small scale, as a result, temperature is elevated. And if your material cannot sustain these elevated temperatures, it basically cannot be used for durable applications. It's not also mechanically robust. So we need a material that can sustain high temperatures, refractory plasmonic materials, which would have adjustable, tunable properties, which would be semiconductor compatible and would have low cost. I want to show with you this Gartner cycle, which was done by my postdoc Orchan Guler on my request. So let me first remind you what this famous hype cycle, which was proposed by Gartner, and it could be applied pretty much to almost any new technology. So normally, if you look at new technology, let's say transistors or lasers, how it would happen, I mean, how it wins the world, if you wish. It starts with some technology trigger, with some discovery, with some first demonstration. Then typically there is exponential increase in terms of visibility. Publications, lay audience, journalists write all these papers, lots of visibility, exponential increase with time. So quite often for new technology, what happens, you reach certain peak of expectations, a peak of inflated expectations. Because once you're overexcited about something, it's hard to avoid some hype. So you face certain problem, and quite often there is a very sharp decrease in interest. Oh, there is certain problem which actually blocks the whole technology. So then there is a decrease in interest toward this particular technology. But then if technology to survive, if eventually really become technology, not just an idea, so you should people come with kind of solution to that problem. Maybe not ideal, but some reasonable solution. Maybe you don't really match the initial expectation, but you find the niche where with this solution, actually this technology could work. Then you have this slope enlightenment. So then it becomes serious. Then people now understand that, yes, it's certainly going to work. And eventually, if everything is all right, you bring it to production. You have this plateau of productivity. In that regard, so let's look at the field of plasmonics generally. So because there are lots of, there is exponential increase in number of publications, lots of interest because it's eventually something what people believe would enable this nanoscale photonics, which is much faster than nanoscale electronics. So lots of applications, and I mentioned many of them. So, and this is of course personal, many people might disagree, but this is our vision at least. We could argue that plasmonics started in 1857, with first demonstration by Michael Faraday how to make this reproducibly these nanoscale plasmonic particles. Of course, they have not even called at that time plasmonic. It was just gold and silver. He used this reduction reaction between two salts. And if you go to a museum in London, you could see still setup which Michael Faraday used to make these colloidal particles of gold and silver by doing this reduction reaction. And the funny thing, we're still doing it the same way when you do it chemically, this gold and silver colloidal particle. So one could say that well, of course, it's maybe frivolous, but one could say that certainly was a very important thing when you, in a reproducible way, was able to make on nanoscale plasmonic particles. Then, of course, you need to excite this plasmon, and initially it was excited with electron beam excitation. People at that time didn't have lasers, so you know, when we already discussed it, when the electron beam goes through metallic structure, it excites these surface plasmons. A very important thing, it was source development in the late 70s and later, surface-enhanced Raman scattering, and people demonstrated, people like Martin Moskowitz or some other people, they showed that when you place Raman active molecules, and Raman scattering is just when you irradiate molecules with light, it's shifted because molecules have these vibrational degrees of freedom, and it's a wonderful fingerprint of any molecule. But when you place these Raman active molecules on rough metallic structures, nanoscale structures such as rough and electrode, then the intensity of Raman scattering increased by orders of magnitude. First, it was misinterpreted when they on the rough electrode, they said, that's because surface is larger, but surface is not that much larger. So eventually they come up with a nice explanation, like Van Dyne, actually, yet another important thing from Northwestern, Martin Moskowitz. So they said that actually it's largely because of very high local fields associated with excitation of surface plasmons in these nanostructures of metal. And because of this enhancement, you have dramatic enhancement in Raman scattering. There's actually lots of interest to use it for all type of sensing, biomedical sensing. It play indeed a very important role in terms of plasmonics. Because of surface enhancement Raman scattering, there was lots of interest in plasmonics initiated at that time. So extraordinary transmittance, like Thomas Edison and other people, they demonstrated when you have in metal film small holes, much smaller than the wavelengths, the transmittance is extraordinarily high because it geometrically should be small by a over lambda to the power 4, where a is the radius of a hole and lambda is the wavelengths. That's an old-known formula written by Sommerfeld long ago, but experimentally they obtained much stronger, and they associated with excitation of surface plasmon. In some cases, localized surface plasmons associated with hole, in some cases, with propagating surface plasmon polaritons. So there are lots of interest toward that. Metamaterials, this notion that you could design and engineer optical properties by changing geometry and sizes of structures, played enormously important role. All this biomedical sensing, nanophotonic circuitry, I told you, this is one of the most important driving force to process information faster on a chip. Plasmonic photovoltaics, already mentioned, spacer, that all was this exponential increase. But then around 2010, our group and others realized, hey, we are hitting the wall. We are using this gold and silver, and they're not the most comparable. They're not going to be used by industry. They're not stable. All these problems I mentioned. So is it just to write a paper, or this is to become a technology? And then several groups, and including ours, we started to work on developing new materials. And actually, a number of new materials have been proposed, including these CMOS compatible, transparent conducting outside, transition metal nitrides, robust, so that can sustain high temperatures. 2D materials came around at the same time. That's very important. because they could help with switching, tuning materials. I showed several examples when you combine graphene with plasmonic structures. So that's all alternative materials, alternative when compared to silver and gold. And they also enabled a number of new applications, such as photocatalysis. We just published, this or last year, I forgot, that titanium nitride could be actually used to dramatically promote the efficiency of photocatalysis. So, and perhaps one of the most exciting things, which is spent quite a bit, that plasmonics and metamaterials could make a difference for quantum photonics. And this is no question about new emerging technology. And when people realize that, it is, again, this is my opinion, but I strongly believe in this, that actually with all this recent development, new material which makes plasmonics real, and with the understanding the fact that plasmonics and metamaterials could significantly enhance, promote key properties of quantum photonics, I think we're coming back to this exponential increase, but now in the context using plasmonics and metamaterials for new emerging technology, for quantum science and technology. So that's kind of interesting observation, which we published a couple of years ago in these Faraday discussions in London, when I delivered this view on the field. All right, maybe I stop at this point, and we consider we continue on Monday. This consideration, that would be concluding lecture for this course within course, kind of overviewing what, based on this background and some fundamentals we covered in the beginning, this overviews of these fields of plasmonics, metamaterials, and its importance and relevance to other fields. Starting from Wednesday, you folks take over. And the first speaker is not here, I believe. Right? Anyway, again, let me repeat. I expect you to attend your group mate's presentation. This is important, to be active, ask questions, and that would be part of your final grade. I will pay attention to this. Thank you. Questions?